Yeah, okay, welcome back. Yeah, today I'm going to continue the thermal property. Yeah, compared to the electrical property, yeah, thermal property is familiar with us. It is because that we already discussed about the temperature effect on the solid material in the atomic scale point of view. I think that almost part is strongly related to the atomic characteristics. So I think that some thermal expansion and thermal conductivity, we already know that detail, but today we are going to discuss about what is the heat capacity, and then some more discuss about the thermal shock resistance for the aerospace devices or some military devices system. So I think that you know that what is the thermal expansion. It is because that the temperature property is strongly related to the atomic vibration motion. Actually, in the 0 Kelvin temperature, atomic has a specific equilibrium distance. It is because that we can decompose to part repulsive interaction and attractive interaction between the atoms. So that due to the when we decompose the two effect, we have a specific equilibrium bond distance which has a minimum energy, equilibrium energies. So, but however, when we increase the temperature from the 0 Kelvin to the for example 300 Kelvin, so that at that time what will be happen? We already know that some atom can has a specific energy. That means that the atom has a ranges of the equilibrium distance. That means that the atom will vibrate. Due to those kind of vibration motion of the atom, so that the equilibrium bond distance slightly increased. So due to some characteristics of between the attractive and repulsive interaction, so that we already know that the thermal expansion and then thermal conductivity, also some transfer of the vibration motion of between the atoms, so that we can easily understand the thermal conductivity. And then the heat capacity. What is the heat capacity? I think that in the last semester, Professor Jung-Hwan Kim already taught you guys about the thermodynamics. At the thermodynamics, I think that heat capacity is a specific fundamental property. How much heat energy can be stored in the solid material. So that's the definition of the heat capacity. However, depending on the environment, for example, fixed volume or fixed pressure condition, we define the slightly differently of the heat capacity. For example, heat capacity at the constant pressure or constant volume, and heat capacity at the specific pressure. Today I'm going to slightly briefly introduce what is the difference. And then so finally, after the covered this fundamental of the thermal property, I hope that you guys know that the exact thermal property on the ceramic or metal or polymer material system. Yeah, let's define the heat capacity. Yeah, in the heat capacity, so the definition of the ability of the material can store heat, absorb heat, or we quantitatively define that the energy required to produce the unit rise in the temperature for the 1 mole of the material. That means that we want to changing of the energy per mole or per gram, depending on your favor. And then to increase the energy, how much temperature must be changed. This is a definition of the heat capacity. Yeah, but we slightly differently define the two way. The first is a heat capacity at constant pressure, and the other is heat capacity at constant volume. Is generally Cp is slightly larger than Cv. So do you know that why it is? So I think that the things, but for you guys understand, I'm going to briefly introduce what is the heat capacity. Just think about, we define the heat capacity looks like this. That means that the energy increased with respect to the temperature changes. So that means that energy will be changed at the constant pressure. So that means that the energy always proportional to the temperature change, and then the heat capacity is a simple linear combination coefficient. But however, we guys know that the heat energy change is a simple summation of the internal energy changes and then work done by external some part. So that so and then, but at the constant volume, so maybe the work is, we can easily define and looks like this. So that means that there are no volume pressure, volume change. That means that we can neglect the work done. No work is done. So we can simply define and looks like this. So that means that the only energy changing effect on the increase of the internal energy, maybe. This is a definition of the heat capacity of at the constant volume. Similarly, we guys can determine the energy changes at constant pressure. Similarly, the heat capacity is simply defined looks like this in the linear combination of the temperature, and then this energy also simple summation of the internal energy changes and external work. So that means that the work can be expressed looks like this. This is a constant, but can be varies. So that means that they have one more term. So that means that the Cp is can be defined and looks like this, maybe. So in the previous slide we defined is a looks like this. So this part is always has a positive value, or so you guys know that how can we know that this is always has a positive value? So just think about, we assume that ideal gas state, PV and RT is ideal gas law. So at the constant pressure part, let's drive the PV, so the PdV and VdP. But at the constant pressure, we can define and looks like this, and also then looks like this, and then after adding to here, Cp and Cv is NR. So R is a gas constant and is a number of the mole, so that means that always has a positive value. So that's the slightly difference between the heat capacity at the constant pressure or constant volume. So please remember those kind of physics unit. Actually unit has same, but the definition is slightly different. So I think that in the thermodynamics class, Professor Jung-Hwan Kim, I think that he taught you those kind of things carefully. After the understanding those kind of concept, so you guys can easily define what is the heat. So without knowing those kind of definitions, so we cannot say that anything. So so in my point of view, to understanding the heat, we must know the temperature. So all energy is related to the thermal energy can be changed to the temperature. So That's why the all thermodynamics first law and second law or some entropy can be derived by some as a function of the temperature. So that's the simple thing. So after knowing that the heat capacity, it can be varies when the temperature will be changed. It is because that the vibration motion is a temperature itself. So if we have a high temperature, that means that we have high energy or high internal energy. So that means that this atom will vibrate more. We have a large kinetic energy. So they will simply proportional to the kinetic energy of the atomic motion, but however that has some limiting value. As temperature increase, the heat capacity will be linearly increased, but however some stages they will show some constant value. So that means that in our previous slide we defined the CV is and looks like this, but we simply think as we have some specific linear equation, but however the heat capacity is varies looks like this linear behavior. So that anyway some constant value will be separate, so that the only important property, the divide temperature. So this divide temperature is some limiting value of the heat capacity will be saturated part. So that's the important thing. But however, we don't need to consider it. It is because that we do not handle the divide temperature anymore. So anyway, from the atomic perspective, so in atomic point of view, energy is stored as atomic vibration. So in other words, kinetic energy. As temperature increases, the average energy of atomic vibration increase. That means that kinetic energy also increases. So the large heat capacity means that the atom can vibrate fastly or largely. So it's the similar word. But however, the atom packed into some constant volume system. At that time, atom has some very high constant pressure, so that the energy increase will be hindered by the closed volume system. However, constant pressure, this volume will breathing freely to keep the constant pressure. So at that time we should consider the more some energy. So that means that that's why the constant pressure shows can suggest the high heat capacity than at the constraint at the heat capacity at the with the constraint of the volume. So anyway, so this is some image of the atomic vibration. Normally we say that the photon is photon is H plus or some light matter, LIGHT matter. We use photon, PHO, photon, yeah. But however, photon is a vibration of the atomic motion. So when you guys can understanding the photon, we can, in other words, we can know that the vibration motion of the atom. So it's strongly related to the dynamics. But after the running of the dynamics in the next year, so we can handle this vibration motion of the atomic scale point of view. So that those kind of atomic scale point of the vibration motion is strongly can be explained as statistical mechanics. So actually I skipped the detail about the static mechanics in this chapter, so that maybe that in the last year I think that I explained some state variable, but I don't know why today I skipped those kind of work. So anyway, due to some vibration motion, some part is elongation, some part is attractive each other. So however, this direction also has some interaction between the x, y direction. So and also the g direction, they have some motion. So due to the complexity of the atomic crystallinity, so that the vibration motion is shows specific shapes. So depending on the shapes of the motion, we normally say that those kind of vibration shapes is mode. So maybe that it will be harder to explain what is the mode, but however, if we have the equation motion as a matrix form, so this x is a position of the atomic point, and then some part can be explained and looks like this. Maybe those kind of atomic motion can be expressed and looks like this. I neglected the c value, so the equal to 0. It is because that we don't have any external forces. However, we can add some energy this part. So at that time, so you guys can do you remember the eigen value and eigen vector from those kind of equation? So this is eigenvector is strongly related to the mode of the atomic scale motion. So after obtaining some specific mode, at that time we can capture those kind of motions. Looks like this. So that mode is a maximum vibration motion of some specific time or specific cases. So that from this mode analysis, we can capture why solid material or atomic structure shows those kind of behavior. But however, depending on the mode shapes, so that the heat capacity, for example CV or CP, can be strongly affected by. But however, we simply say that the heat capacity is simply linear proportional to the temperature changing with the energy with respect to the energy changes. But this energy can be explained by the kinetic energy of the atomic scale point of view. But let's skip the detail. But anyway, so based on those kind of insight from the atomic structure, so the polymer and ceramic metal has a different crystalline structure. So that metal has a well-ordered crystalline structure, so that there are no big movement. However, ceramic structure will be strongly affected by it is because the plus and negative ion, positive and negative ion, if they vibrate, they are strongly affected to the next to the atom. So that means that the vibration is strongly propagated to the another atom. So the heat capacity is slightly higher than. But the polymer, we do not explain detail about the polymer. However, polymer interaction is very weakened, or between the atom connected the chain, they have a very strong binding energy, but between the chain at that time they have a weak vibration, weak bonding strength. So that means that they can easily vibrate more. So the heat capacity is slightly higher, twice larger than the ceramic or metal system. Although I say that ceramic shows a higher energy capacity, but it's not always correct. So some metal, for example aluminum, shows a very high heat capacity, so that it's not truly say that the ceramic always higher capacity than the metal side, but the polymer always higher heat capacity. So please think about why polymer shows a high heat capacity than the ceramic and metal system. So the all affected by the bonding difference. So next, let's discuss about the thermal expansion. We guys know that what is the thermal expansion. When we increase the temperature, the atom will vibrate more due to they will gain higher kinetic energy. So they have a large velocity, so that they can more vibrate more. But however, let's go back to our previous chapter. So for example, so here, if we have those kind of symmetric potential energy curve, although we have a increased energy state, the atom will vibrate more largely. Okay, we can agree with those kind of vibration motion. But however, due to the large vibration, we cannot say that what is the equilibrium bond distance, so that we say that the center point is equilibrium bond distance, so that zero state and R1 and R2 and R3 always has the same center point. That means that when we increase the temperature, the atomic bond distance, equilibrium bond distance, always constant. That means that there are no thermal, we cannot expect any thermal expansion, those kind of energy potential curves, so symmetric curve. So, but the real atomic environment curve, energy curve, and looks like this. This energy curve axis symmetric curve or unsymmetric curve. So it is because that the repulsive interaction is very proportional to the 10 to the minus 50, or this part is 10 to the minus 6 or 12. So that attractive forces and repulsive forces has a different strength. So we finally obtained those kind of axis symmetric curve, so that when the temperature increases, the center point is shifted and looks like this. So that equilibrium bond distance when we increase the temperature, so that we can expect the thermal expansion. But also we cannot, it is hard to say that all atom environment has those kind of axis symmetric curve. Sometimes they have those kind of symmetric curve. So at that time, so we can expect a small volume expansion, but normally we have those kind of largely axis symmetric potential energy curve. We can obtain the thermal expansion anyway. After the understanding those kind of physics phenomena, when we increase the temperature, finally the final length of the solid structure can be increased. Looks like this. So that finally, if we have a large size of solid structure, that means that the temperature is slightly higher than the initial state. So that those kind of way we can determine the thermal strain. We use TH as a subscript, so that the strain can be expressed the length changing, and then with respect to their initial lengths, so that this is a thermal strain. And then those kind of thermal strain is simply linear proportional to the temperature changes. So the temperature changes can be expressed T final minus T initial. And then alpha is a simple linear coefficient. So the linear coefficient of the thermal expansion. So some linear coefficient means that some material shows a non-linear coefficient of the thermal expansion. At that time we can explain that those kind of thermal coefficients will be varies as a function of the temperature, in like the Cp and Cv. So that. But however, the most solid structure shows a simple linear thermal expansion characteristics. So that those kind of way we can explain, we can define the thermal strain. Let's go to the next. That's right. So in here, yeah, let's compare to the various material. Yeah, in the thermal coefficient of the polymer shows few hundred value per Celsius or Kelvin, but metal or ceramic shows a very small thermal expansion. It is because that the plus and minus ion in the ceramic structure, they will strongly attract to each other. So that means that the attractive force is very large, and then the repulsive interaction is very similar. So that means that in the Lennard-Jones potential curve means that the attractive force is very weak and repulsive force is very strong. But however, due to the different Coulomb interaction, so that attractive forces is also strong, and then repulsive also strong when then very close contact each other. So that means that we can easily expect that their energy curve is similarly symmetric shapes, so that we can expect it very small thermal expansion. But when we increase the temperature, the vibration, we can expect it very large vibration motion, but the thermal expansion is small. But anyway, metal shows some weak axisymmetric behavior, but the polymer attractive is weak. It is because that the metal anyway, they has a metallic bond, but this between the polymer, they shows a secondary bond. This is a very weakest bond characteristics, so that means that the polymer will show a very large axisymmetric behavior, so that as a conclusion, the thermal expansion of the polymer is very large. So please explain those kind of questions. So let's check some example. Copper wire, which has 50 meter long, is cooled down from the 40 Celsius to the -9 Celsius. How much change in the length will shows? So let's discuss about detail. So how can we say that the initial length is 50 meter, but the total length changes, we do not know the final. Initial is 50 meter. This is a thermal strain. This thermal strain is simply linear proportional to the temperature changing, so that the initial, so how can we say that the temperature change is cooled down, so that final and initial, so the Celsius. So those kind of way we can easily determine, but before we start, we must know that which one, thermal coefficient of the copper. So maybe that the copper has those kind of value. So I already prepared those kind of thing. So I think that that's the correct thing one. But anyway, let's think about the L final is plus alpha is 65 10 to the -6, and then 50 and then -49. So I think that in this here, so they use a positive value, but I will have a negative value. So it is because that they think about the temperature length changing is positive, but however, just think about the cool down means that we can expect the shrinkage of the copper wire from so that I think the delta L will always has a negative value. So that I think that this is equation more correctly. So that means that the 50, this is will become answer. So those kind of way. Next thermal property is thermal conductivity. Yeah, we know that the thermal conductivity, thermal conductivity can be expressed Fourier's law, so that conductivity like diffusivity can be simply proportional to the temperature changing. So, and then with the thermal linear coefficient of the thermal conductivity, but this temperature changing also affected by the length changing, so that in other words, temperature gradient is linearly proportional to the heat flux. So there are other similarly the diffusion flux J simply expressed the gradient of concentration or conductivity of the sigma simply proportional to the potential gradient. This is a electrical property. So the similarly Fourier rules expressed and look like this. If we have a temperature difference, heat must be flow from the high temperature to the lower temperature. That also strongly affected by the lengths. If they have a short lengths, the heat must be flowed very fastly, but they have enough long passes. At that time, the heat flux can be slowly. So the atomic perspective, the heat transfer can be explained by the atomic transference of the atomic vibration or free electron. So that in other words, cooling means that the vibration motion can be reduced. So if in these stages the vibration very fast and large, but in this stage the vibration small and weak. So that during the heat flux, that means that the kinematic energy can be transferred to the another atom state, another atoms. So those kind of thing, it is because that the atom is connected by some bonding networks. So that this also can be strongly related to the binding of their electron state. So that's why they mentioned the free electron. So that generally metal shows a very high thermal conductivity. So that means that during your cook the meal, so that in the hot pot, so that your spoon or knife, we feel the very high temperature. That means that aluminum steel glasses shows a very high heat conductivity, but compared to the metal, so the ceramic structure, for example, silica. So silica is glasses. The glasses shows a slower heat transfer, and also polymer. So that maybe that your substrate for your hot spot we use as a polymer material or wooden material for the heat insulator material. So that it is because that the heat transfer means that they must be connect each other. Atom must be connected each other. So that metal shows easily vibrated their motion to the another atom with a very high bonding strength. But the polymer, although in the chain they have a strong covalent bond, but however between the chain they have a weak binding. Although this polymer can be largely vibrate, this vibration motion energy cannot transfer to the another chain. So that's the reason the thermal conductivity of polymer shows a very small. But in other words, ceramic, so atomic motion also they will show. It is because that they strongly attractive and repulsive each other. But compared to the metal system, metal has a free electron. So this means that the vibration motion and furthermore electron can freely move to the another side. So that this, due to the adding this free electron, their energy state is strongly increased. The vibration motion can be enhanced. But in the ceramic state, the electron always localized between the covalent bond system. So anyway, those kind of reason the metal, ceramic, polymer shows a different characteristics in the thermal conductivity point of view. Yeah, based on our summer characteristics, we can also define the summer stress. It is because that stress is a simply linear proportional to the Young's modulus and strain. So we define the strain, summer strain, so that when we use those kind of strain can be written or expressed by the summer strain. At that time, we can say that this stress is a summer stress. But please remember that the pre-summer expansion does not generate any stress. Yeah, those kind of summer stress always generated due to the large constraint. Actually, some solid copper wire located between the two walls. This is a copper. Their initial temperature looks like this, and then when we increase the temperature, at that time this copper wire won't expanded. This is a we can expected the summer strain. However, due to the rigid wall system, although they won't expanded those kind of amount of the lengths, but however they must go back to this site. So that means that this amount we should push to this wall may be the push this solid copper wire. Due to the reaction process, this solid copper wire will experience some stress. So at that time we call it the summer stress. So without the wall, although that this copper wire expanded, their stress in this region is equal to 0. It is because that there are no forces at the surfaces. So please remember that although sometimes we have a summer strain of some solid structure, but it's hard to say that that summer strain generated some stress. So without the constraint, those kind of wall or some physical constraint, summer stress does not arise. So for example, in here, brass rod. Brass is some dong, maybe in Korea. So the stress pre-stated, there are no constraint in here. So that the temperature 20 Celsius, but it heated up. That means that they will increase more. So that what temperature does the stress reach minus 172 megapascal. So it's hard to say that if this environment is does not have any external geometry, so that although we increase the temperature, the stress always equal to the 0 without the constraint. But we assume that due to the temperature increase, we obtained those kind of summer strain, and then we compressed this heated brass rod to their initial state. So that without those kind of constraint, it is hard to say that this solid will experience some summer stresses. So anyway, so due to this strain, the compressive strain will show the negative direction. So finally, the Young's modulus and negative summer. So that's the reason, the summer stress generation. So that those kind of way, so we obtain finally the kind of result. Maybe 170 megapascal, 10 to the 6 pascal, and brass Young's modulus we should check the 100 gigapascal 10 to the 9 pascal, so that we can cancel out the alpha. Before we start, we should know that the alpha coefficient here 20 10 to the minus 6 per Celsius or Kelvin, similar. So that this is finally we want to know that initial is 20 Celsius, so that finally we can easily obtain the 106 Celsius. So this is the simple example. Yeah, so you guys can know that the why summer stress is generated. So that without any constraint, although we increase the temperature, solid material does not experience any summer stresses. But the summer shock resistance also has a similar concept. So those kind of summer shock resistance occurred at the non-uniform heating or cooling state. So it is because that if we increase the temperature slowly or cooling down the temperature very slowly, at that time there are no shock summer resistance. But sometimes we rapidly cool down or rapidly increase the temperature of the solid material. At that time, some surface region, their temperature extremely changed very fastly, but inside part keep constant their initial temperature. So at that time, this solid part will experience a large summer strain. When we assume that the past cooling down, that means that this surface part experience rapidly shrinks, but this subtracted part keep constrain their initial lengths, but to shrinkages. But however, this subtracted catch in the upper surface part. That means that they cannot shrink, but they want summer strain. For example, those amount of the strain, but they want to shrink and looks like this on the subtracted, but however they connected each other. That means that they pull out, looks like this. Those kind of amount can become the summer strain. So that maybe that this part we experience the summer stress to this direction. Maybe that we say that tensile stress. Compared to the previous example, the experienced some compressive stresses, but however, so in here they will expected, we can expect the tensile stresses on the surface part. So that temperature difference can be arised those kind of tensile or compressive stress depending on the direction of the temperature changes. So that however, due to the rapidly changes of the temperature, so that surface part will experience the very high shocking or large stresses. So that due to the large stresses generation, this solid part will be broken. Some crack will be initiated or propagated. So that those kind of way, so we should control the quenching rate. Quenching means that temperature cooling rate. So that this pressure stress, maybe that looks like yield stresses. We have some criteria value, so that sometimes the temperature changes exceed those amount of the differences. So at that time, this surfaces part will be experience very large pressure. So that those kind of way. So we should define the quenching rate can be simply proportional to their yield strengths and Young's model, inversely proportional to the Young's modulus, and thermal expansion coefficient, and then some quenching ratio. But this case, it's the meaningless. It is because a very artificial value. So anyway, based on those kind of relationship, we should design the synthesized processes for some solid material system. So this is the concept of the thermal resistance. If we have a large thermal shock resistance TSR value, at that time we can use those kind of material to some space shuttle, or it is because that they need a high thermal shock resistivity. It is because that during the trip on the spaces, universe, at that time they will experience the very large temperature changing on the atmosphere. So the maybe that this part in the front part, so we use a very high heat resistive material. So the in the early this year, Professor Yang and me collaborated each other for some project, the military academic department, so that we designed some epoxy and POS system. This POS system is a silicon oxygen 3D structure atomic system. They will have a very high thermal resistivity characteristics, so that the polymer, we easily know that the very small heat conductivity, large heat conductivity and the heat small resistivity, but and then they can easily decompose at the high temperature. However, if they cross-linked each other, we can obtain the very high heat resistive polymer system. So the Professor Yang and me simulated the thermal characteristics of the POS embedded the polymer system for those kind of space shuttle or military system. So it is because that in the missile they will also need some the heat resistive some solid material on their cases. So anyway, silica tiles also used well known for the space shuttle, and that their microstructures is 90% is over porosity. It is because that the air has a very poor thermal conductivity characteristics. So that solid material has a very higher conductivity, although that we say the polymer poor ion thermal conductivity, but compared to the gas or liquid phases, the conductivity of the solid material shows a very big high value. So that to reduce the thermal conductivity of the solid material, we must contain the very large void spaces, but we can increase the thermal resistivity characteristics, but due to the large pore, we lose the strength mechanical characteristics. So that there are some pros and cons between pros and cons to design those kind of solid material. So then in the plant system also experience very large temperature changing from the off state and to the operating state. So that maybe that there are some very large product, for example, how can I say that, the Hwan, maybe I forgot the exact name in English, but they will experience a large thermal strain or thermal resistivity, so that we should design for the plant, we should use a thermal resistive solid material for the constructing the plant summer for the summer energy. So this is the end of today's lecture. This is a summary. We learned about what is the heat capacity, and then I also explained that depending on the constraint, volume and pressure, their heat capacity is slightly differ. And then we also learned about the thermal expansion again, and then conductivity and shock resistivity. So to explain that the thermal expansion, we should know that the vibration motion in the atomic scale point of view, and then the bonding characteristics also affected to the conductivity of the solid material. And then after the covered these two topics, we learned about what is the thermal shock. So those kind of thermal shock can be arise from the extremely large temperature changing, for example, the space shuttle or missile systems. So that at that time the surface part will experience a large shrinkage or expansion than the core part in the subtracted part. So they will on the surface part, they will experience some fracture. So that to overcome those kind of things, we should design the solid material properly. Maybe that we should increase the high strength mechanical yield strength, or to decrease the reduce the Young's modulus or reduce the thermal coefficient. Thermal expansion coefficient. So there are many strategies to reduce the TSR property, but I'm not sure that which is the best strategies for the to reduce those kind of thermal shock resistance. But however, if you have any idea, please notice me anytime and you want. 모두들 수고하셨습니다. 다음 시간에 뵙겠습니다.